Hello and welcome. Imagine stepping outside your front door, but instead of a street, there is nothing. No air, no sound, no pressure. The temperature can swing from being hotter than boiling water in the sunlight to colder than Antarctica in the shade. This is not science fiction, this is the reality of space. Before we can understand how NASA keeps astronauts alive there, we must first understand what we are up against. Space is a deadly void, and our bodies are not built for it. We are fragile beings, evolved for a very specific, comfortable planet called Earth. The first and most immediate danger is the lack of atmosphere. On Earth, we are constantly under a comfortable blanket of air pressure. This pressure does a critical thing: it keeps the fluids in our bodies in a liquid state. In the vacuum of space, where there is no pressure, these fluids would start to boil. Not from heat, but from the absence of pressure. Your saliva would boil on your tongue. Beyond that, there is no air to breathe. Within 15 seconds, the oxygen left in your bloodstream would be used up, and you would lose consciousness. The vacuum would also cause your body to swell, though your skin is tough enough to prevent you from bursting. It is a gruesome and quick end. But that is just the beginning. Without the protection of Earth's atmosphere and magnetic field, astronauts are bombarded by radiation. On Earth, we get a little bit of radiation from the sun, but most of it is blocked. In space, astronauts are exposed to much higher levels from two main sources: the sun, which can unleash violent storms of solar particles, and galactic cosmic rays, which are incredibly high-energy particles coming from outside our solar system. This radiation can pass right through the skin, damaging cells and DNA, which increases the risk of cancer, radiation sickness, and long-term health problems. So, the challenge for NASA is monumental. They have to create a tiny, portable, and perfectly functioning piece of Earth. A spacecraft must provide air, pressure, and protection, all while hurtling through this most hostile environment. It is the ultimate life support system. So, how do you protect someone from nothingness? You build a wall. For astronauts, that wall is their spacecraft, whether it is the International Space Station, a capsule like Orion, or their spacesuit. These are not just metal containers, they are sophisticated, pressurized bubbles of life, meticulously engineered to replicate the essential conditions of Earth. The first and most important job of this bubble is to maintain a stable, breathable atmosphere inside, while the deadly vacuum sits just inches away on the other side of the hull. The primary structure is built to be incredibly strong and airtight. Even a tiny crack or a pinprick hole could lead to a catastrophic loss of pressure, an event called decompression. To prevent this, modules are often built with multiple layers of shielding. The outer layer deals with the threat of micrometeoroids, tiny specks of space dust that travel faster than a bullet. An impact from one of these could be devastating, so spacecraft often have Whipple shields. This is a clever design where a thin outer bumper sits a distance away from the main hull. When a micrometeoroid hits the bumper, it vaporizes, spreading the energy of the impact so that only a harmless cloud of dust and gas hits the inner wall. But the shell is more than just a physical barrier. It also has to deal with the extreme temperatures we talked about. Spacecraft are covered in a blanket of special materials called multi-layer insulation, or MLI. If you have ever seen the International Space Station, it looks like it's covered in gold foil. That is MLI. It is made of multiple thin sheets of plastic coated with metal, like aluminum or gold. These layers trap heat, acting like a giant thermos, keeping the cold of deep space out and the comfortable temperatures generated by the crew and their equipment in. Together, this strong, insulated, and sealed shell creates the fundamental pocket of safety, the very first line of defense against the void. It is the barrier that allows all the other life-saving systems to work inside. Inside our protective bubble, we now need to fill it with a livable environment. The two most immediate human needs are air to breathe and water to drink. You might think NASA just launches giant tanks of oxygen and water, but that is incredibly inefficient and unsustainable for long missions. Instead, they have developed brilliant, closed-loop systems that recycle and reuse these precious resources, much like a miniature version of Earth's own ecosystems. Let us start with the air. The air we breathe is not just oxygen, it is mostly nitrogen. But in space, to simplify the systems, the atmosphere inside a spacecraft is often maintained with a higher percentage of oxygen at a lower total pressure, or a Earth-like mix at a normal pressure. The real trick is managing the composition of this air. When astronauts breathe, they consume oxygen and exhale carbon dioxide. If CO2 builds up, it becomes toxic. So, the station uses a machine called a carbon dioxide removal assembly. It pulls in the cabin air, uses special materials to scrub out the CO2, and then vents it overboard into space. But what about the lost oxygen? That is where the magic happens. On the International Space Station, the oxygen generation system takes water sent from Earth and, through a process called electrolysis, splits it into its two base elements, hydrogen and oxygen. The oxygen is pumped directly into the cabin for the crew to breathe. This leads us to water, which is just as precious. The water recovery system on the station is a masterpiece of recycling. It collects every single drop of water it can find, not just from the drinking water supply, but also from urine, sweat, and even the moisture from the crew's breath. This dirty water goes through a multi-stage purification process that involves filters, a catalytic reactor that breaks down contaminants, and finally, a system that removes any remaining particles and bacteria. The result is water that is purer than what most of us drink from the tap. By recycling over 90% of their water, the station drastically reduces the amount that needs to be launched from Earth, which is astronomically expensive. This cycle of air and water is the beating heart of the life support system. We have our bubble, our air, and our water. But there is an invisible enemy that our metal walls cannot completely stop: radiation. As we travel beyond the protective magnetic bubble of Earth, the threat from solar radiation and cosmic rays becomes the single biggest challenge for long-term human survival in space. NASA's approach to this problem is a multi-layered shield, combining monitoring, shelter, and smart planning. The first line of defense is constant vigilance. NASA and other space agencies continuously monitor the sun for signs of solar storms, huge eruptions that send a flood of high-energy protons towards Earth. When a major storm is detected, mission control is warned. The astronauts on the space station are relatively safe because it still orbits within the partial protection of Earth's magnetosphere. But for future missions to the Moon or Mars, this would not be enough. For those scenarios, the spacecraft would need a designated storm shelter. This wouldn't be a special room, but rather an area where the walls are the thickest, perhaps surrounded by the spacecraft's water supply, food, and other equipment, which can all act as additional radiation shielding. Speaking of shielding, this is one of the toughest engineering problems. You cannot just wrap a spacecraft in a thick layer of lead; it would be far too heavy to launch. So, scientists are investigating new, lighter materials that are better at blocking radiation. Some are testing plastics that are rich in hydrogen, as hydrogen is very effective at scattering incoming radiation particles. Another fascinating idea is to use water or even human waste as a shielding layer around the crew's living quarters. For future moon bases, one of the best solutions might be to simply live off the land, by building habitats underground, using lunar soil, called regolith, to bury the structures and provide several meters of natural protection. The fight against radiation is a constant balance of weight, technology, and prediction, ensuring that astronauts are not silently accumulating a dangerous dose on their journey. The spacecraft is now a safe, well-supplied home. But there is another, more subtle danger that comes from the very thing that makes space amazing: microgravity, or what we often call zero-G. Floating might look like fun, but for the human body, it is a signal that something is wrong. Our bodies are built to work against gravity. Our muscles, our bones, our heart, and our blood circulation all depend on that constant pull. When that pull disappears, the body begins to deteriorate in ways that are startlingly fast. Without the need to stand or walk, your leg and back muscles begin to weaken and atrophy. More seriously, your bones also get the message that they are not needed. Cells called osteoclasts that break down old bone become more active than the cells that build new bone. This causes astronauts to lose bone density at a rate of about 1 to 1.5% per month. On Earth, an elderly person with osteoporosis might lose that much in a year. This also leads to a release of calcium into the bloodstream, which can increase the risk of kidney stones. Your cardiovascular system also gets lazy. The heart does not have to work as hard to pump blood to your brain and legs, so it weakens. Fluids, no longer pull downward, shift toward the head, causing that familiar puffy face look, and can also affect vision. So, how does NASA fight this? The answer is a brutal and mandatory routine of exercise. Astronauts on the space station exercise for at least 2 hours every single day. They do not use normal weights, because lifting weights in 0G is useless. Instead, they have specialized machines. The primary one is the Advanced Resistive Exercise Device, or ARD. It uses powerful vacuum cylinders to create resistance, simulating the act of lifting heavy weights, doing squats, and deadlifts. They also use a treadmill and a stationary bicycle, but they have to be strapped down to them to create resistance. This intense daily workout is not for fun, it is a critical medical countermeasure to prevent their bodies from wasting away, ensuring they are strong enough to return to Earth's gravity and walk on their own when they come home. We have tackled the physical threats, the vacuum, the radiation, the bodily decay. But there is one final, crucial element to keeping an astronaut alive: their mind. Imagine being confined for 6 months or longer in a small, metallic can with a handful of other people, floating 250 miles above Earth, with no way to step outside for a change of scenery. The psychological challenges of spaceflight are immense, and for a mission to Mars that could last 3 years, they become as important as any engineering system. NASA takes the mental health of its astronauts very seriously. Astronauts undergo intense psychological screening and training before they are ever selected for a mission. They are taught conflict resolution and stress management techniques. On the space station, mission control psychologists regularly check in with the crew. The station itself is designed to help. They have a cupola, a windowed dome with a breathtaking 360-degree view of Earth, which serves as a priceless psychological refuge. Contact with family is prioritized through video calls and emails. They have a regular schedule that includes work, exercise, personal time, and even weekends to help maintain a sense of normalcy. Looking to the future, for journeys to Mars, the systems we have discussed will need to become even more advanced and self-sufficient. The life support systems will need to be nearly 100% recyclable in what are called closed-loop or regenerative systems. We might see greenhouses growing fresh food, which not only provides nutrition but also offers a psychological boost. The spacecraft will need to be smarter, with AI systems that can help diagnose problems and even perform automated repairs. Ultimately, keeping humans alive in the deadly void of space is the greatest team effort. It is a symphony of engineering, medicine, psychology, and human courage. It is about taking a tiny piece of our world and carefully, miraculously, carrying it with us into the great, dark unknown.